Hello, everyone. Thank you. First of all, thank you all for coming here. So, as Sebastian was saying, so I am a cryptographer, and for the last few months, I've been working with the HOPR Association, analyzing their protocol. And today, I'm going to talk to you about my findings and what is actually this layer 0 privacy protocol does. So, since we are in Paris, City of Love. So I'm gonna give you a simple example of a love story. It's not Romeo and Juliet, it's a different story. So you all can follow through and understand what's happening and how this communication goes through HOPR in a private way. So we have Alejandro who has a crush on Zoe, and he needs to send her a love letter anonymously. He doesn't want everyone to know about it. So he asks a bunch of people to help him to send this letter. So we name them Betty, Chow, Dimitri, and they send that letter, and then they get paid for that. So just for the context, we use names of people here just to explain the story and make it easy to understand. But in real life, we're actually using anonymous nodes, and no one actually knows the other one and who actually sent that message and who actually receives it. So to start with, let's talk about data privacy issue. So privacy, we all hear a lot about privacy and how important it is, how important is data privacy, metadata privacy, but why actually is that important? So we think of data as something that identifies people. So something that's like, for example, name, country, address, everything that's about us, about the hospital record, any type of information, work, all of that. So there are two types of information. We have data and metadata, and basically metadata is data about data. So you might think of it as something not that important, but it's actually very, very important. And there are big companies, big corporations who actually understand that value of that metadata and use it in different ways. Sometimes it's not harmful, and sometimes it's actually harmful. So let's take an example of two people communicating. So as I said, Alejandro and Zoe, so they usually use direct connection between them, but because we are in the 21st century, for these people to communicate, they will actually use different platforms. It's like Facebook, Instagram, all these different platforms, which we call as third parties. So these third parties will help these people communicate. However, these third parties will have access to all that type of information, like I said, address, for a list of friends, pictures, all that sort of type of information. But can we actually trust those third parties? Or maybe they can be hacked, or whatever. We are in a, I guess since you are in an Ethereum conference, you basically understand the value of decentralization and not trusting third parties. So you must understand the value of this. Now, why metadata must stay private? Like I was saying. So does anyone really understand why that is important? So just think about it. Your IP address is actually metadata. Think of someone who actually knows where you live, where you send your transaction from, where you buy, where you're sitting when you buy your ETH, where you're sitting when you buy your Bitcoin. All of that sort of information. Can that be dangerous and trustable for other parties to know about that? So metadata says a lot about human beings. So it's highly valuable for advertising companies because they use it to send advertisements for people to send, for example, to buy products and all that, which not exactly is harmful. And when it's not collected, it's not that harmful. So you think of it address, and someone else has sorry for that. So when all that data is not collected together, it's not that harmful. But think of someone, some entity has all that data together. It can understand your behavior. It can understand everything you're doing and control your behavior, which is very dangerous. And metadata actually has less legal protection than data. And it's, of course, it's a huge power over behavior. So What is the solution? So in HOPR, we propose a solution using different entities, different relayers, and we call them multi-hop. So multi-hop routes. So instead of sending a direct message, we use multi-hops to send that message. So think of it as a direct connection like this. However, so we want to, of course, to unlink sender and receiver, and we don't want their identity to be known. And we want these people who help, and these, let's say, relay nodes who help doing so, of course, relay and make that unlinkability and not get that link, which is quite complicated. Because we have two different issues. The first issue is third-party, like global passive adversaries. Let's say, for example, governments or any adversary who has control over the whole network can see everything that's happening over that network. So even if there is no direct communication between one party and the other, still having that multi-hops can make us go through the whole path and find actually who sent a message to whom. So the solution is using mixed nets. So mixed nets means that we're, instead of sending a direct message, we're mixing it into different directions. And so instead of sending it from A to B to C, so we're mixing that and putting it in a black box and then sending those different messages in parallel. And that would make it really hard to link those two messages together. Now, the second problem is those relay nodes that we're actually using, they actually know some type of data. So they know to whom they're sending, they know the address of the receiver, and we don't trust them either. So the idea of this is to actually make no one understand more than they need to know. So the solution to that is the Sphinx packet format, which I'll speak about later. So basically this protocol helps us hide any type of unnecessary information from these relay nodes, and they would only know the address of the next relay node and not know anything more than that. So we will do that by encrypting that data, and then and then they will not find the address of the final receiver. So if we go through the first solution, like I said, MixNet. So MixNet, they protect against powerful GPA, so powerful adversaries. So it's that what differentiates them from Tor. I don't know if you ever used Tor, but that's something that makes MixNet better than Tor, because Tor, it only protects from local adversaries, and if someone controls the whole network, they cannot protect over that. So it links via packet mixing, so packets are being mixed. So instead of sending a message from Alejandro to Betty, and then from, for example, Ciao to Zoe, so these messages and packets are mixed inside of black box, and then they're sent afterwards, which make it really hard to understand who sent a message to whom. So you see it, it could be like a simple example, but when you have a big network, then it becomes really hard to track these messages. So we add to that, basically, we unlink these messages, and then we add the delays and cover traffic. So what I mean by cover traffic is that think of the messages that we have are in yellows, so these packets, and then everything is blue, is basically cover traffic. So cover traffic is just basically random noise that we add to the network, which makes it hard to track the messages. So when we add noise, this random noise will not allow us to track whether message 1 went to destination 2 or went to destination 3 or 4. And then we add delays. By adding those delays, it makes it also hard to do attacks on the network and to know if the message was sent at this time, was it actually delivered at the different time, or was it delivered right after that. So by doing that, we provide a larger set of anonymity and of course make it more secure and private. And like I said, imagine it as a big network. So when you have a big network and you're having all these nodes doing cover traffic and all these nodes helping to send messages, then we have more privacy to the network. And it's a decentralized network of nodes which are anonymous, and they don't know one another in this network, and they basically just relay packets. Now, to explain what is actually the Sphinx, which solves the second problem, meaning that relay nodes should not know more than they need to know. It's actually it provides onion encrypted payload. So like I said in Tor, so instead of sending a message, we encrypt it in an onion shape way. So you have layers of encryption, and each relay node actually has one key to decrypt one layer. So until it arrives to its final destination, and then it's completely decrypted, and the message can be read by the final destination. So that's something we have in the Sphinx. And then packets basically are indistinguishable from one another, and they all have the same size. This way we cannot conduct any type of attacks based on the size of the packet. So let's say if a message has this size and a different message has a different size, then of course it's easier to track down these different packets. But because we pad them all to the same size, then it's harder to track them down. And also we use a header. That header we send in its different type of information, like the address of the receiver, which I'll explain later, and it will be encrypted. So this is how the Sphinx packet format looks like. So we have a header and we have an onion encrypted payload where the actual message is. And in the header, we have 3 steps: the key derivation, encrypted routing information, and the integrity tag. So the first one we mean with it is that there is a key derivation process between the sender and every relay node to extract a shared key between all of them. That shared key will be used afterwards to encrypt routing information. So each relay node, when they receive that routing information, they can decrypt one layer, and then they send it to the other relay node. And in that routing information, there is the address of the final receiver of the payload, basically the packet. So so this means relay nodes cannot know that address until it arrives to final destination. The last relay node will know that it's sent into the last to the final destination. And then the integrity tag, basically it would allow us to assure that that header was not changed at any point of time by any relay node, and basically the same message that was sent by the sender, it stays the same. And basically the payload, which is the actual message, is also encrypted. The integrity is being encrypted by lioness encryption method, which I will not go into, but basically we cannot change that message at any sort of time. And if it is changed, then it just becomes a random data that cannot be readable. So the key derivation process, as I said, is basically just normal Diffie-Hellman process that goes offline between the sender and every relayer. So that's Betty, let's say the first relayer, and then using Betty's public key, and then the public key that Alejandro will have, they will create a shared key together, and that shared key will be used to blind, or let's say encrypt, the routing information. And that this process happens with every relay node in this network, let's say in this channel where the message is being sent to packets. Now, okay, let's say now we have this privacy protocol. Now we can guarantee that messages cannot be readable. We cannot know, we cannot link the sender to receiver. That's cool. But as I said, it's something similar to Tor or maybe to other projects in the system. But however, of course, there is some differentiation between Tor because it doesn't protect from global adversaries, but there is also a different issue, incentivization. So if you ever used a Tor node, I don't know if any one of you has ever run a Tor node, but why would you? I mean, you're not paid for it, basically. You're just doing it because you believe in privacy and you're doing it, but you're spending your own money. So, and in Tor, basically, it hasn't scaled for the last few years. Because basically the problem is we do not incentivize these people to actually transfer and create these nodes in the network, which will increase the anonymity set to be used in the network. So we are a believer that Tor is great project, but we think that it can be definitely improved by adding incentivization and paying these people who are providing this great job, of course. So we need to add incentivization. So why would, hey, we say Alejandro's friends, but again, like I said, they are not his friends, it's just for the story. So why would they transfer the message? So they need, so we want to create an incentivization system that's censorship resistant. So it's completely decentralized. Let's say we're using it on Ethereum, for example, and it's efficient. So in layer 2, so it's layer 2 protocol, so it could be efficient, and also it's privacy preserving. So we use these payment channels to do so, which I'll explain later on how we use them. Now, our approach basically to the incentivization system. So first of all, nodes should only get paid if they actually did a job. So we should not pay these nodes without them doing any job. So it becomes harder to attack the network when nodes actually provide a value and do a job, and then they get paid. So the second thing is that we need to verify if they actually did a good job or not, if the final receiver actually received the message untagged or not. So this verifiability, of course, it needs to happen, and that the payment needs to happen using, let's say, a trusted third party, emulated trusted third party, like something like Ethereum. So it could be transparent, and everything that's happening on that network, we can see it, is that when people actually provide a job that's verifiable, then they get paid for it, and they don't get paid if that's not the case. So we use our proof of relay in HOPR. So where, of course, we have proof of stake, proof of work. So we have here proof of relay. So when you prove you have done relay in the network, then you get paid. So how does this happen? So let's imagine a node. So I am a relay node, and then I want to get paid in this network, of course. So I would create a key, basically SI0, which is not the same key that I showed earlier in the key derivation part. That basically was the master key that's used in the Sphinx header, and then we create different subkeys. Each subkey will be used for a different case, and of course we don't use the same key just because it gets hacked, for example. These subkeys get hacked or they get revoked, so we need to have a subkey for each different case. So we have a subkey that's created by the first relayer. Then that relayer would receive another key, SI+1, from the next downstream node, so the next node after them. And that actually, the key would prove that, okay, the next node actually received the message. So when the next node receives that packet, they send back this value, which then we compute a response to receive a payment. So that response will be to a challenge, which I'll explain later, which basically would help these nodes respond to a certain challenge to get paid in the network for their relay and service. Basically, then the downstream node can verify the integrity of packets and payments information before handing back that key half. So basically, the next downstream node would verify that it was untagged using the integrity tag, and then sending back that half key. And of course, this way, it would allow us to make sure that the packet was transferred correctly. And of course, by not receiving that value from the next downstream node, it means that the packet will be dropped, and that relay node cannot receive any payment for their service because, of course, they didn't receive from the next downstream node a validation for that. So this is how to visualize this to understand it even better. So the same characters that we used before. So basically Alejandro and Zoe in order to connect. So when the payments cannot be redeemed by any party unless they receive, we use it as a key. So basically that's a half key that's sent by the next downstream node to the one before, and then payments can be redeemed by the one before. Okay, now talking about these payments. So the idea is, of course, we want to pay these different relay nodes for their services, but we don't want payments to leak any metadata, and we don't want it, of course, to be costly. So that's why basically we're using payment channels because and using probabilistic payment channels because basically that would allow payments to be redeemed after some point of time. So not every payment will be redeemed after every relay that's been done, just because we're using probabilistic micropayments, and it would mean that not every relay would allow a node to access a payment, which means it's only probabilistic. That would incentivize them to continue relaying basically, and in order to get paid. So let's say you send 100 packets. So from those 100 packets, when some other node would relay them, they would only get paid, let's say, for 10 or 15. So since they don't know which one will actually provide a payment or not, they will just continue relaying that. And payments will be redeemed at the end, so that will not be costly, of course, on chain. Now, what I was saying, I said, as I explained it later, before, sorry, as a half key that's sent by the next downstream node. Here we explain it as an acknowledgement. So the acknowledgement means that, okay, I have received the packet and I send my acknowledgement to you back. Now you could redeem the payment. The problem is in proof of relay, these acknowledgements might lead to dependency graphs. So we have, let's say, A, B, C1, C2, C3. A wants to send 3 packets. So he wants to send to C1, to C2, to C3. So he sent these 3 packets. B is only a relay node in the process. So basically, C1 will send back the acknowledgement to B. That acknowledgement one that they have received the packet. C2 will send also, C3 will send also. Let's say acknowledgement one was not received by B, so that we have packet loss, for example, here. So acknowledgement was not received by B. Or maybe acknowledgement 2 was received before acknowledgement 3 was received. Here we have this problem. So in case packets are lost, or we have a different order of receiving acknowledgements than the order of packets. So we need to provide a solution for that. The solution for that is basically using what we're using in HOPR. Basically, these independent, so acknowledgements are completely independent from one another. But as well, if you it's the addition. So acknowledgement 3 will have the payment for acknowledgement 2 and acknowledgement 1. So even if packets, if the acknowledgement 1 was lost, by providing acknowledgement 3, and even if 2 was received before 3, when it's received, it has the addition of all the values of payments that should be received by these packets. Now, it's not charging. Can you go to a different slide, maybe? Try. Yeah, was this the slide that I was going to present? Can you go back?
Yeah, it's the one after the...
Yeah, the one after?
It's the one after.
Ah, okay, so the one after.
Yeah,
sorry. Internet issues. Okay, so now that I talked about these acknowledgements, now we have 2 other problems. I hope everyone is following. A lot of issues, right? A lot of problems we're trying to solve. So Two problem is that the upstream node can try to cheat to make every, so here we introduce a different concept called tickets, and tickets are basically just tickets for payments. Tickets will be later on redeemed as payments by these different nodes. So what if the upstream node actually try to cheat and make those tickets always lose tickets? So make that relay node always losing, and because I said it's probabilistic payment, and not every payment provides, and not every packet provides an actual payment. So in order for us to prevent from that happening, we introduce commitments. So a commitment, what does it mean? It means that the upstream node, it will create this random value that it will need to use to calculate the winning, so whether a ticket is a win or not. And that value, it will commit it. So it computes the hash of it and commits it on chain. So it means that it can never change it afterwards. So when it can never change it afterwards, which means that it can never change whether a ticket is a win or not after it's committed that value. The second issue is that the downstream node, so the node after that, could try to cheat and make every ticket a win. So in order to prevent from that happening, we introduce a different concept called hints, and basically makes the sender. You remember that the sender creates shared keys with every node in the process, every relay node. So basically that sender will provide that shared key from the next downstream node to the node before that as a hint. So it will compute it, it will provide it not directly, but it will be multiplied by a generator of elliptic curve. And that hint will basically be used to make sure that the value cannot be changed. The value of acknowledgement that it's sent back cannot be changed, which means the winning, whether a ticket a win or not, it cannot be changed basically from neither the upstream nor the downstream node. So it could be hard probably to understand, but that's basically what's happened. So we have the commit and the reveal process. So when committing that value, basically the generated value to calculate whether a ticket is a win or not. So it's committed on chain, that entropy. And then when a node needs to reveal that and to redeem their ticket to win, of course, to win, let's say, HOPR tokens. So basically they would reveal, the sender, the upstream node will reveal that already committed value. And then tickets will lead to a win if this is the case. Basically, the hash of that commitment, of the previous commitment, with the response that I explained as the half key of the relay node and the half key of the next downstream node. So basically, if we provide the previous commitment with that response and the signed ticket, basically the ticket needs to be signed by the sender of that ticket. So if this hash is less than the winning probability, then that ticket would lead to a win. Now, the next thing, as I said, the hint, which would make the downstream node not be able to cheat and make the ticket always a win. So basically, the sender will provide this value, SI plus 1, multiplied by a generator of elliptic curve that we're using. So that we call the hint. So it's the value that we're supposed to receive from the next downstream node. And then when we have that hint, basically, we can respond to a challenge. A challenge basically is the value that the relay node is providing, and plus the next downstream node providing, all multiplied by the generator. So if we have the hint, basically, relay node will only provide their value multiplied by the generator and do the addition of that. And that it could respond to a challenge. If the challenge cannot have a response, or the response doesn't match with the already provided hint, basically this packet gets dropped and will not be sent afterwards to other relay nodes. Now, going back to the Sphinx packet format, like I said, in the header, basically we have the payload and we have the header. In the header, I said we send the destination's address. We send we also add some padding to make all these packets have the same size, and we also add, so it's a modified version that HOPR is using of the original Sphinx. So we add the hint and the challenge values to the Sphinx header. So these hint and challenge that I explained. And basically there is a hint and a challenge to every relay node. So every relay node, when they receive this header, they will decrypt, they will unblind this header, basically to know what is their routing information, what is the address of the next relay node, and basically the hint value that they would have for the supposed to be value that they should compute to solve the challenge. If they cannot solve the challenge, they will drop the packet, and the packet cannot be sent else afterwards. And also there is an identifier, which is basically we're not currently using our HOPR. It's used for single reply blocks, which is in Sphinx, but we're not currently using in HOPR, probably in the future. Okay, now explaining basically the tickets, like I said. So ticket has to have to be issued by someone, basically the sender of the packet. So the sender of the packet will issue a number of tickets in this. When they create a channel of communication between sender and receiver, they will generate amount of tokens, of tickets, sorry. They will sign those tickets, and then those tickets get to be validated afterwards by every relay node. And then when every relay node presents a response, and that response actually matches with the challenge that is they supposed to solve, basically that ticket is being validated and the packet is not being dropped. And then when they want to redeem that ticket afterwards to get HOPR token, then of course they provide the acknowledgement from the next downstream node, and they solve that challenge and they get back their ticket. So if you see, the acknowledgement is sent, for example, from D to C. So it's from the next downstream node to this node to acknowledge that they actually have received that packets. So another issue also, so what if we double spend tickets? So what if these tickets can be spent several times by every relay node? So in order to solve that, we basically introduce ticket index, so which are stored in a smart contract. So this ticket index will increase by every time ticket is being redeemed, and basically tickets cannot be spent twice or several times. And also other current limitations to the protocol. So basically the current payments payments protocol that is used in HOPR leaks the position in the relay chain. So in order to send payments, so basically the first relayer here in the example, let's say, would receive 3 hoppers, and then the second relayer would receive 2 hoppers, and the third one only 1 hopper. So not all of them receive the same amount, and basically by having that different amount, their position in the channel will be known. So we know that the one that received 3, for example, is the first relayer, the other one is the second, and the other one is the third. So that can, a solution to that, this amount could be obfuscated, for example. Another limitation is that downstream node might not hand back the key, so the acknowledgement key. A solution to that is just basically closing the channel and blocking redeeming those tickets. So that node will not actually win anything. So because when they don't send that key back, basically they're not going to be paid afterwards for relaying packets. Another limitation is that anonymity sets by using all these relay nodes has to be bigger, and we need to incentivize more and more nodes to join, and we need to create a healthy topology. And basically, we're adding covered traffic allocation to the network. So the more covered traffic we have, the more anonymity set going bigger, and of course, it's getting harder to attack such a network. Going back to our story, Alejandro and Zoe, basically, they have a happy ending. So she received his letter. Basically, they fell in love. The others had tickets to go to Rihanna or whatever artist you want to go to, or they want to go to. I am a fan of Rihanna, so they went. They gained concert tickets, and everyone is happy. So that's cool. Okay, so I take this opportunity because I'm presenting today to tell you that the HOPR staking program has actually started today on the 20th, and people can lock their stake in the HOPR protocol, and basically can redeem rewards starting from the 27th of July. And we also have an NFT program which will boost the base of staking. So these people who will stake, they will gain NFTs. So check it out. Go to our website, check our Medium article, which I'll show the link about, to understand more how our staking program works. Basically, there is no picture of me, sadly, but I'm here. Basically, so it's a small team, 19 members already in the team, and we are all over the world. Well, not really all over, but yeah. Anyway, maybe all over continents, except Africa, sadly. Okay, so with small team, we are believers of privacy. We are here today to share with you our project, and looking forward to get questions from you, to get people to interact with us, to understand more about what we're doing. So you can find the link to the yellow paper, basically the technical paper of the protocol, on GitHub. So it's not completely finalized, but anyone can see it. You can also see the staking program, HOPR staking program, on this link. And of course, you have links to the Sphinx package format and also to Mixnet if you're interested. If you're also interested in our project, you might go and see tomorrow my colleague's talk, So she will be talking about our DAO experiment in HOPR, so how we use DAO. So that will be tomorrow, 6:20 p.m. In the same room. So go there to understand more about the DAO that we're using. And that's it. Thank you so much. Do you have any questions?
Hi, Harry from NIM. So,
Hi.
I don't even know where to begin. Let's start with the cover traffic. So, your network does something called free routing, right? So you can just choose your route as long as you want. And that's a kind of known, not super anonymous design. And you say, well, we can fix it using cover traffic. Now, unless I'm mistaken, with that design, as your network gets larger, the amount of cover traffic has to continually increase, right? So let's say I'm sending one real packet to be kind of anonymous. I'd have to send 10 packets. And let's say I send 2 packets, and it's like nonlinear, right? So it's going to go to like 30. Do you see any other ways to deal with that problem of scaling?
I mean, I can leave Sebastian answer to this question. He's basically the one working on cover traffic.
Yeah. So, I mean, you're right? In a naive implementation, HOPR would just distribute like this thin traffic. Now, the thing is, that's not what we're doing. Like, the cool thing about what Amira presented is we didn't talk about what topology we're using. We didn't talk about the traffic allocation. So effectively, you can run very much like a layer topology on top of HOPR. You could run effectively on top of HOPR. You could allocate your traffic to as many nodes as you need to receive sufficient traffic that you can obviously still afford, because, traffic has to come from somewhere. And lastly, on this topology, you could even build like super crazy stuff like loopback traffic. All of that is something that you could do with HOPR being basically a Mixnet toolbox for you. So we didn't talk about the details here. We're going to experiment with various designs for it. But yeah, basically, HOPR is open to implement whatever works best.
Thank you. Any more questions? Okay, then thank you everyone, and happy conference, and welcome to Paris. We are distributing t-shirts next to the room, so you can get some yellow t-shirts. If you're not tanned as me, so it will not look beautiful, but whatever. Okay, so thank you so much. Enjoy your stay here. Bye.